Welcome back to The Explainer. Today, we're diving into a concept from complex mathematics that is just as powerful as it is, well, beautiful. We're talking about analyticity.
So you probably think you have a pretty good handle on what a smooth function is from your days in calculus, right? But in the wild world of complex numbers, smooth takes on a whole new meaning. It's a level of smoothness that has some pretty profound consequences. Okay, let's get into it. So let's really nail this down. When we talk about analyticity, we are going so much further than just saying a function has a derivative at a single point. No, we're talking about a much stronger and way more demanding kind of smoothness. And this right here is the absolute key. Analyticity isn't about being smooth at one single lonely point. It's about being perfectly smooth in an entire area around that point, a whole neighborhood. It's a way stricter condition, and you know what? That strictness is exactly what gives these functions their incredible power.
To really get a feel for this, think about it like this. A function that's just differentiable at one point, that's kind of like finding a single smooth patch on an otherwise bumpy road. But an analytic function? Oh, that's a brand new multi-lane superhighway. It's perfectly smooth in every direction as far as the eye can see.
And what happens when a function is analytic everywhere? I mean, across the entire complex plane? Well, it gets a special name. We call it an entire function. And the poster child for this is the good old exponential function, e to the z. It's a mathematical superstar.
Okay, so why should we care so much about this super smoothness stuff? Well, because being analytic isn't just some fancy label. It's like a VIP pass that comes with a whole toolkit of powerful, predictable properties that make these functions incredibly well behaved. Yeah, these analytic functions are a great team. You can add them, multiply them, divide them, and you know what? The result is still analytic. They basically form this exclusive, well-behaved club where everything just works.
And check this out. This is where that predictability really shines. You know how in calculus you sometimes run into those nasty indeterminate forms like 0 divided by 0? Well, for analytic functions, there's a rule for that. There are no surprises.
Let's walk through a classic example to see just how cool this is. So we've got the limit of sine of z over z as z goes to 0. You plug in 0 and you get 0 over 0. Looks like we're stuck, right? Wrong. Because both sine of z and z are analytic, we can just whip out L'Hopital's rule. Take the derivative of the top, derivative of the bottom, and all of a sudden the limit is just 1. It's beautiful.
Okay, that's all great, but how can we actually tell if a function has this amazing property? Is there like a test? You bet there is, and it's brilliant.
Say hello to the Cauchy-Riemann Equations. These two little equations are basically the bouncers at the door of club analyticity. If a function's real part, which we call u, and its imaginary part v, can satisfy these two conditions, then you're in. The function is analytic. It's that direct.
But where do these rules even come from? What's the logic? Well, it all boils down to one simple, powerful idea. For a complex derivative to truly exist, the answer you get can't depend on which direction you approach from. The path can't matter.
So imagine you're walking on the complex plane towards a point. If you decide to come in from the side, purely horizontally along the real axis, the math gives you this expression for the derivative. Okay, but hold on. What if you took a different path? What if you came at that exact same point from the top, straight down the imaginary axis? You get this totally different looking expression. Now, for the derivative to exist, it has to be the same number, right? It can't matter which way you came from. So you just set the two expressions equal. The real parts have to match and the imaginary parts have to match, and voila, the Cauchy-Riemann equations pop right out.
Let's put this test to work. First up, z squared. We run the numbers, and boom, perfect match on both equations. It passes with flying colors. But now look at the complex conjugate, z bar. We check the first equation, and right away, we hit a wall. 1 does not equal -1. So, sorry, z-bar, you are not analytic. It's that clean.
All right, get ready, because this is where things get really cool. All this abstract math we've been doing, it's about to connect to something you might actually recognize from the real world, from physics and engineering.
Let me introduce you to harmonic functions. Basically, a harmonic function describes a state of perfect balance, or equilibrium. Think about heat spreading through a metal plate. Once it all settles down, the temperature at any given point is just the average of the temperatures right around it. That's a harmonic function, and it shows up everywhere in physics.
And this is the mind-blowing part. Every single analytic function is literally built from two of these harmonic functions. The real part, u, and the imaginary part, v, are both harmonic on their own. The two concepts are deeply, fundamentally linked.
And the proof isn't some super complicated page-long monster. It's actually shockingly elegant. You just take those Cauchy-Riemann equations we already know, you differentiate them a second time, do a tiny bit of algebra, and Laplace's equation just pops right out. It's an absolutely stunning connection.
Okay, we've gone through a lot here, so let's step back and ask the most important question. Why does any of this matter? What's the big picture takeaway?
Well, what analyticity gives us is a completely new standard for smoothness, one that's amazingly predictable. It hands us a toolkit that makes complex calculus manageable. It gives us a clear-cut diagnostic test to identify these special functions. And maybe coolest of all, it builds this profound, completely unexpected bridge between the world of pure math and the physics of our actual reality.
So if you think of math as the language that our universe is written in, what secret is analyticity telling us? It kind of suggests that the most stable, well-behaved systems we see in nature might all be governed by this deep, fundamental principle of smoothness in all directions. It's definitely something to chew on. Thanks for watching.